Steve, do you want to be up here, shake some hands with the teams, or? Sorry, I couldn't hear you. Do you want to be up on the stage, shake some hands with the teams? I think that would be good. I think you have invested really a lot of time here.
Stay in the general area, and then when you announce them, or just. Okay. Go down. Yeah.
All right. So basically, welcome back. Welcome to the last act of the Capstone project class. We've basically had a number of judges that were using a list of criteria to look at the different projects, and then we created a score and then averaged it out, and then found out that things were very, very close. It was really, the teams were doing an outstanding job, were great presentations and great projects. So this was definitely not a very easy decision. And there was a lot of discussion also among the jury members to make sure that, everybody sort of agreed with the final ranking. But of course we can only pick 3, so in the end, decisions had to be made. The way we want to do this is, of course, there is a prize money, there will also be certificates, but we can't give them to you just yet because we basically just made the decision literally 15 minutes ago. So we will have those certificates by the end of next week, and once the winners have been announced, Greta can wire the money to you. So you will get, of course, your prize money, and you will get certificates, but we just can't give them to you now. However, what would be great is, we announced the teams from 3 to 1. If you could just come up here, we'll just shake your hands and then make a couple of pictures, and you can get your deserved applause from the audience. All right, so with that and without further ado, let's jump into this. In the jury's mind, the third prize goes to a team Not Our Sac Fault, sponsored by Nova Coast. Awesome. Congratulations. Good job. Congrats. Now you guys could still hear and just the congratulations. Clean. Over here. Okay. Yeah, just Steve on the right, I'm on the left, and then.
Ashlyn and Clara had to go to a quiz, so
okay.
They are not here.
Awesome. Thank you very much. All right, and that came with a prize of $500. Now we move on to team number 2, and the prize of $1,500 goes to Shrewd Farms, sponsored by Invoca.
Thank you.
Congrats. Great job. Congratulations. Congrats. Congratulations. Congratulations. Closer. Okay, congratulations again. All right, and the first prize, number one, and $2,000, and the winner of this year's Capstone project competition is Stage Presence, sponsored by LogMeIn. Delicious. Good job. Good job. Awesome job. Awesome. Thanks again. Great job, guys. All right, so much about Capstone competition and the winners. We'll now start with the Distinguished Graduate Student Lecture Series. As I mentioned at the beginning, there will be 5 talks, TED-style talks about cool research that happens in the graduate program UCSB, and like the Capstone competition, we will give awards out right before the distinguished lecture. And the first one, Victor, just set it up and then.
Is it on?
Wait, it takes a little bit, now it's on.
Okay.
Okay, and he's talking about Lockborg, express your persona without revealing your location.
All right, thank you so much. Hello, everyone. My name is Victor Zachary. I'm a PhD student in Distributed Systems Lab. Today I'm going to talk about our work, Lockborg, express your persona without revealing your location. This work is in collaboration with my lab mates, Chetan and Theodore, and our advisor, Amla Abadi. It is currently being implemented by Ray Tang and Ishani Gupta. So the goal of this work is that we want to give the social network users more control over their privacy, and specifically in this topic, location privacy. And I have to say, at the beginning that our, oh, this is not on? Okay. Yeah, I have to say at the beginning that our technique is more in client focused, so we think about developing software systems that sits beside the client, help them fight their privacy battles on the web. But just to get you more engaged in what is the problem, I'll bring some news from the Russian hack on the US elections, and we can see how micro-targeting on social network can be used in a bad way. So these are like some of the news that were published in 2016 and 2017. And it's talk about like the Russian campaigns are being targeted to some specific states like Michigan and Wisconsin, or some groups, anti-refugees in swinging states, or some combination between like your ethnicity and your locations. It's like Black Lives Matter in Baltimore and Ferguson. And these are just some news about how micro-targeting can be used to do bad stuff. Also, the other thing that I want to point out about location is surveillance. So surveillance on social networks is happening a lot, and these are like some of the news that also in 2016 and 2017 that were published, and says that the police is using surveillance on social networks to track activists. And there are some systems like Geopedia. It's just an online social network tool to analyze the location of the users. And it was used to target basically the activists of color. So by knowing their locations, they can be targeted. So when I started this project, I looked at what Facebook knows about me. And I invite everyone in this room just to go and see that in your profile. So if you go into settings, ads, your information, new category, you will feel what I felt, that Facebook knows too much about us. So this is just a snapshot of how they categorize you. And nothing is surprising. All this information were provided by you. Like you give them this information, but what is bad about it is that it is used as an ad category. So for example, away from family, away from hometown, frequent international traveler, long distance relationship, it's all like, oh wow, that's too much. So it felt like, oh my God, you know too much, guys. And if you look here, most of these categories are based on location. So they know our location, and this can be used against us in micro-targeting. So if we look in abstract how the users are represented and how this attack could happen, so a user is represented as a vector of attributes. It could be like gender, ethnicity, location, political point of view. And the social networks or the attacker are trying to understand these attributes about all the users. They can be used, as we mentioned before, for like micro-targeting and other stuff. And this information can be known using the content that you produce, like you write about things, and from this content I can understand your attributes. Or from your followers and friend network. So for example, if all your followers or friends are from California, most probably I will guess that you are also from California. So in this talk, we focus only on the content-based analysis. Like we are trying to protect users against content-based analysis attacks. And to understand how does it work, so I will give you an attribute inference example. So this was published, this is a previous work that was published in DBSec 2017 that shows that basically we can use the attributes that we know about different topics to understand the properties or the attributes of individual users. So if we look here, we have 4 topics. And we can know the attributes, like, for example, the location. So topic 1, Boston refers to the location that tweets the most about topic 1. And it's usually by liberals and females and etc. You can apply that on all the topics. So now if we have 2 users, Alice and Bob, and we only see what they write, their content. So how can we understand their attributes based on what they write? Basically what we do is that we run some statistical analysis. We say, okay, if Alice is tweeting about topic 1, I have some confidence that she is female liberal in Boston with some probability based on 1 tweet. And then Bob's the same thing. I can have like some guess about their attributes, either they're conservative and male. And then if we aggregate that over many, many topics, I can just get more confidence about their attributes. So for example, if I see Alice is tweeting about T1 and T4, my confidence gets up that she is female. While if I see Bob tweeting about T2 and T4, I will get more certain that they are conservative, but my confidence about their gender goes down. And this is what we call content-based inference or attack. And here we focus about the location. So first, what are the user's privacy options? We assume that the user is not giving their location for free. We assume that the user is trying to collaborate with us, with our tool, not to give their location to the social network or the attacker. So we assume that they hide their IP using some obfuscation technique like Tor browser, and they turn off their location so their tweets are not geotagged. And then, but still we can face the content-based attacks. So you have either the option to write about nothing. If you write about nothing, I won't know anything about you, so no information. Or you can write about everything, like generalize in all the dimensions, write about all the topics of interest for all genders, all ethnicities, all locations, all political point of view. But if you do that, your profile won't be interesting at all. It's not capturing your what we call online persona. There's no personality here. So what we want to do is we want to give the users tool that allows them to generalize the location while preserves their online personality. So we want to generalize only on the location dimension, not on all the dimensions. So the goal is to hide user location while maintaining their personality. So how does it work? So this is a system. We assume we have the client, and we assume that we have the adversary who can see the public tweets that are tweeted by every single user. If we consider the adversary also the Twitter itself, they can see more than the public tweets. But in both cases, it doesn't matter. So, and then there is Logborg. This is a software system that we develop that sits beside the client trying to help them hide their location. So how does it work? So this is a data flow. So Logborg is continuously doing topic analysis on what are the topics that are being discussed on social network. And then when a user writes a post, for example, the crowd at JFK Terminal 4 chanting, which side are you on? Hashtag no Muslim ban JFK, no Muslim ban. What Logborg is going to do, first, we are not going to post this tweet immediately. But what we are going to do is to say, okay, hey, you're writing about this topic, and this topic could reveal your location. We will bring you some other topics, some other hashtags that are being discussed on the network that are talking with your interest, but from other locations. So for example, here we bring 2 examples, one from LAX and one from Denver Airport, that is talking about the same hashtag. Maybe this hashtag is not discussed in other locations. So what we are going to do is to bring you something that is of your interest from other location. So we suggest that to you. So the user sees these suggestions and say, hey, I want to write about a couple of these suggestions. And what Lookborg is going to do is going to queue all the posts, and then over time is going to send them randomly just to destroy the time distribution of the original posts versus the obfuscation posts. So typically what happens is that in location obfuscation, what is usually used is what we call blind generalization. So for example, if we're using a location-based services, Google Maps, and I want to get the nearest gas station, there are two ways to do that. I can say, okay, what's the nearest gas station to myself? But by doing that, I reveal my location. Or I can say, okay, I will generalize. I will ask about listing all the gas stations in California and filter in the client. I will explain why we call that blind generalization. By doing that, you didn't actually hide your state-level location. So if you want to hide your state-level location, you make this rectangle wider, so list all the gas stations in the United States, and then filter in the client. Okay, what if we use this similar technique in our case? So in this example, we have the US map, and we have different circles with different colors that represent different personalities. And we could have contradictory personalities, like the red people with no band, no wall, while the blue people are build the wall. And if we just generalize your profile with all the people in the States, yes, it will secure your location, but you have lost your personality. You are being generalized among people that are contradictory with your opinion. So what do we aim to? That's what we call blind generalization. So what our technique aims to achieve, what we call selective generalization. I want to hide you among all the people who are aligned with your personality but are in other locations. So basically, we'll find other people in other locations that are aligned with your personality based on our analysis of your personality, and then bring you the topics that you're talking about. So how would you choose the obfuscation locations? So one way you can say, okay, for every tweet you're writing, we'll bring 4 other tweets from any random locations and suggest that to you. But by doing that, what could end up happening is that your location's original location is L, and for every tweet, we bring you a different set of locations that is randomly chosen. So what can happen is that this technique is vulnerable to statistical attacks, and the reason is that the L, your original location, is more common in all the obfuscation groups. So how could we get around that? What we do is that we use a fixed set per user, fixed set of locations. And we choose this fixed set of locations that has similar personality like the user we want to hide the location. So, for example, here we have California, Texas, Illinois, and Montana. And we want to achieve what we call K-location indistinguishability. So what do we mean by that? Is that for every tweet that you're going to post, the same set is going to be used to hide the location of this post. And the goal is to have something like that. Is that the confidence of the attacker about your original location and other locations are equal, so they will not be able to distinguish which location are you in. So the takeaway of this talk is that surveillance, tracking, and micro-targeting are happening, and users need software systems to help them fight their privacy battles, and users should have more control over their privacy in the attribute level at different granularity. So in the location, it could be in state level, it could be in city level, it could be in country level. And Lookborg is just the beginning. We are just starting to develop a set of tools that will help the users achieve these goals. And with that, I would like to thank you and take any questions.
All right, any questions for Victor? No, all clear. Tawfiq, very good.
So the statistics you gather, I assume, also change in time, whereas you set this up. So do you, at some point, so do you constantly update the statistics based on what is being observed?
Yes, so that's a very good question. So we observe what the users are writing, and we update. So basically, you could think of it like the obfuscation technique is using the attack to understand what the attacker will understand about myself, and then based on that, we'll suggest other topics, and then run the attack again, and then see if we achieve this K-location distinguishability or not. Thank you. That's a good question. Yes.
Hi, Victor. Thank you for the good talk. My question is about the selector generalization that you were talking about. Mm-hmm. So in this example, you said that you generalize over, you don't want to lose the personality of you being red, but what is the level of granularity that you end up using in your system? Because I'm assuming there are a lot of traits that define a personality. So which are the ones, or how do you select those traits?
So the technique is independent. You can run it on so we are developing like the algorithm and the data structures to do this obfuscation. So the technique is actually independent, but what we are using is gender, ethnicity, political point of view, and location. These are the four. Yes. And the location is currently in state level, but you can dig deeper and say, okay, maybe we want like city level, Santa Barbara versus Chicago or something. Yes, that's a good question. Yeah.
When you suggest alternative tweets for the user, how do you make sure the content mentions the same thing? Like, do you only change the hashtags?
So it doesn't have to mention the same thing. I think what it have to mention is, I'm not sure. We are running the attacks based on hashtags, yes. So I will bring you hashtags that are aligned with your personality. So if you are an African-American female Democrat in California, I'll bring you topics of interest for African-American female who live somewhere else. In terms of hashtags, yes.
Yeah, but then you don't suggest the user alternative tweets, right? Like you don't.
It's not alternative. I don't want the user to change their tweets. I want them to write what they want to write, but also write other things such that when you run the statistical attack over all the tweets that you tweet, it will end up that the locations are indistinguishable.
Okay.
Yeah.
Thanks.
Great. Okay, one last question in the back.
Hi. So I assume that certain like topics may be heavily focused in like a geographical area. So like if I say like fire or flood or something, and you might be like only Santa Barbara has that. So then how would you create, like how would you get a tweet for that from somewhere else?
So you don't have to get a tweet about the fire or flood.
Mm-hmm.
I will get a tweet that is aligned with the personality of the person from another location that could be also in another focused community.
Okay.
And actually there are research that has been done to get the topics of interest to focus community. It's not like the wide area trending topics, it's just for focused groups. So there is research that's done using that, so we can just plug this to our technique in terms of the suggestion.
Okay, thank you.
All right, and I think with that, let's thank Victor. Thank you.
Thank you so much.
Okay, next up is Niraj. I think the title is Shortest Path with Twists and Turns. Is that roughly correct?
Yes.
Perfect.
Hello everyone, welcome to my talk. I'm Neeraj, third year PhD student working with Professor Subhash Suri. I'm going to talk about geometric shortest paths with some interesting twists and turns. Okay, I will save the twists and turns for later, and I will just start with shortest paths. Okay. So the problem is we are given a source and a destination, and our goal is to find shortest path between them. For instance, in Google Maps, we input the source address and the destination address, and it finds us the shortest path between them. Okay. So what happens behind the scene is we map it to a graph problem. Okay. So all the traffic intersections, they become nodes, and all the roads connecting those intersections, they become edges. And then with each edge you assign a cost, which is basically the time taken to travel that road or the distance. So the problem in the problem of shortest path in graph is a classical problem, and there are very well-known algorithms such as Dijkstra and Bellman-Ford to name a few. Okay? But one interesting thing is, shortest path in graphs only changes at discrete intervals. Okay? So we are interested in problems where paths live in continuous domain, such as geometric spaces. For instance, movement of humans, or a robot, or a drone, or ships and airplanes. Okay? So how do we find shortest path in such spaces? Okay? That's the question we are asking. So for now, we will only focus on the case in 2 dimensions, where we are given a bunch of objects in a plane, and for instance, a campus map, and we want to go from point S to point T. Okay? So of course, the problem becomes interesting only if there are obstacles, that is the regions that you cannot go through, otherwise you can just walk in a straight line. Okay? So we have 2 distinct regions, obstacles and free space. So obstacles could be buildings, no-fly zones, etc., and free space is everything else. We want our path to lie in free space. So if we start by modeling our obstacles as polygons, which gives us a nice looking picture like this. So we have polygonal obstacles, n vertices, source S, target T, and we want to find the shortest path which avoids all the obstacles. Okay, as you may have guessed, this problem is very basic in computational geometry, and therefore very well studied. And there are fast, theoretically optimal algorithms known for this problem. So what do? So here comes the interesting twist that I promised. In the classical version, all the obstacles are fixed. So what if you can remove obstacles from input? Of course, if you remove obstacles from input, your free space increases, and therefore you can make the shortest paths even shorter. Okay, but you don't want to remove all the obstacles. So you want to remove a small number of obstacles k, and you want to shorten the shortest path by maximum amount. Okay, so which is cool, but why do we care? So, and turns out this problem has applications. So for instance, so far we have been dealing with shortest paths in a fixed network. But what if shortest paths are not good enough? What if shortest paths are still pretty long? What can we do about that? So, and what if we are allowed to change the environment? What changes should we make? We want to make a small number of changes so that shortest paths are as per our requirement. Okay. This has applications in urban planning, so we can add shortcuts in a congested neighborhood, or we can reconfigure road network by adding flyovers. Or an application is in a warehouse-based setting where there is a robot which moves around obstacles, and then we can reorganize the layout so that the paths are shortened for the robot. Okay. So far we have established that the problem is interesting. And now in the next few slides, I will go into the details of the techniques we apply and the results we achieve. So back to our original framework, polygonal obstacles with n vertices, source S, and target T, and integer parameter k. We assume that our obstacles are convex and non-overlapping. By convex, I mean all the angles are less than 180 degrees. And we want to remove k obstacles so that the path is shortened by the maximum amount. Well, so a naive solution is just try all possible choices, remove them from input, and compute the shortest path in the remaining domain. Okay? But as you may notice, that quickly runs into a problem because we have way too many choices. So reasoning about removing obstacles directly leads to combinatorial explosion. What we do instead is we do not remove obstacles, we just allow paths to cross through them. Okay? And then our question changes to this. We want to find the shortest path from S to T that goes through at most k obstacles. If you look closely, these two questions are equivalent because we remove all the obstacles that are crossed by the shortest path, and that is the minimum number of obstacles that we need to remove. So we'll refer to a path that crosses k obstacles as the k crossing path. And in the next few slides, I'm going to show how do we compute the k crossing path efficiently. So now we come back to interesting turns. Observe that although the space of paths in this world is infinite, the path only turns at a few interesting points, which are the obstacle corners. So, and this also applies to k-crossing paths, and this gives us a nice way of mapping our problem as a graph problem. So what you do is you make all the obstacle corners as vertices, and you add edges between each pair of vertices, okay? And you assign them the number of obstacles that they cross. So you only add edges as long as the segment crosses fewer than k obstacles. So this gives you a graph which has quadratic number of edges, and each edge has a length L and a parameter J, which is the number of crossings. Now what you want to find is, you want to find shortest path from S to T in this graph, such that the sum of crossings of its edges is less than K, okay? And this seems a lot like shortest path problem in graphs with an extra constraint. And indeed, one can apply the graph algorithms to solve this problem in time, which is Kn square, which is still quadratic in n. Typically, k is small, the number of obstacles that you need to remove are small, although n can be large. So even for small k, this algorithm might not be good enough. For a reference of how it can be, on the extreme left we have the solution that is the least we can do, and on the extreme right we have the theoretically best solution. What we achieve using this technique is Kn square, which lies somewhere in between. And for moderate values of k and large values of n, this can take a few hours. Okay? So what we achieve is not theoretically optimal, but it's pretty close to it. And the running time is k square n log n, and the details are outlined in our paper, and they're quite technical. So in the next few slides, I'm going to go into just the intuition behind that algorithm. Okay? So the first question that we ask for the speed up is do we really need to build a graph? Okay. If you take a step back and see what we did, we took a problem with linear complexity and we created an artificial graph which has quadratic number of edges. So anything that we do on this graph is going to be stuck with a quadratic complexity. So what we need to do first is we don't need to use a graph, and instead we should exploit the geometry of the problem. And turns out there is indeed such a solution which has inspiration in physics of wave movements. So imagine you have a lake which is stationary, and you have a bunch of floating objects that are also stationary, and you drop a pebble at the source S. So what it does is it creates ripples. These ripples are, imagine, unit speed ripples, and they move from the source. So after a time t equals to delta, so the boundary of the wavefront is basically the set of points that are a distance delta from S. Okay? So if you keep propagating these ripples in the space, when they hit a corner of an obstacle, new ripples get created, and these ripples, they contest for the free space. Okay? So all the paths in the green region must go through U, all the paths in the gray region must go through V, and similarly if you keep propagating them, what you get is called a shortest path map. So this map is really interesting because for each region there is a unique predecessor. So if you want to find shortest path to a target T, what you can do is you can find the region in which it lies and find the predecessor and simply backtrack to compute the shortest path. Okay? So all our algorithm does it simply simulates progress of this wavefront. But we have one additional challenge. So the challenge is, since our paths can cross obstacles, these ripples, they can also cross obstacles, but they can only cross k of them. We show that despite this difficulty, we can do all of this in time k square n log n, which was what we promised. Okay? So, which is all good, but there is a little caveat. So observe that every time a path crosses an obstacle, our algorithm counts that obstacle. Okay? So which means that if our path cross the same obstacle twice, we'll count the same obstacle twice, and which will mean our results would not be correct. So the question is, can the paths cross the same obstacle again? And fortunately, the shortest path would never do that, as our obstacles are convex and non-overlapping. Which means that whenever such a thing happens, there must exist a shortcut that must lie entirely inside the obstacle. Okay? Interestingly enough, the problem gets really challenging in general case because the paths can cross the same obstacle again. For instance, if the obstacles are non-convex or the obstacles are overlapping. Okay? And surprisingly, the problem becomes NP hard even for simple objects such as squares when they are overlapping. Okay? So the question we are asking is, what is the best we can do in such situations? So in such situations, we are okay with a solution which is not too bad, or an approximate solution. So the question we are asking is, what if we run our algorithm that we just came up with on overlapping instances of unit squares, for instance? How bad can that solution be? If you look carefully, we can show that shortest k crossing path can cross a unit square at most twice, or else you can make it shorter. Okay? So, which means that if the optimal solution removed k obstacles, we come up with an algorithm which will remove at most 2k obstacles. So this is called a 2 approximation in the algorithms community. Right. So what we did was we started with a new direction in geometric shortest paths. We came up with a clean formulation with removable obstacles motivated by applications. We designed fast algorithms exact wherever we can, or else we come up with approximation schemes. And this opens a lot of new directions for further research. For instance, what about removable obstacles in 3 dimensions? Or what about surface of a terrain? So you can imagine you have a hill and you want to construct a tunnel. You have 2 choices, either to go over the hill or go inside the tunnel. So what is the cost of creating that tunnel? Should we or should we not? And then the final question is, what about approximation algorithms for more general shapes which are not just unit squares? Okay? And with that, thank you.
Any questions?
Niraj, really nice talk. So I have 2 variations of the problem that I think would be very interesting. I just want to know if you have looked at them. One is if you have multiple trajectories instead of just one.
Say that again.
You have multiple trajectories. Like now you're trying to optimize one path, right? What if I have 100 of them?
I see.
And the other one is if you can just get rid of an object, you can just move it somewhere else. Have you looked at these problems? Do you think that it will be much harder than the ones that you have looked at?
Yes. Actually, the question you're asking with multiple destinations is the current problem that I'm working on, and it seems pretty hard. So I don't really have an answer as to what can we do about them. So it seems like the problem could be NP hard, but we don't know yet. And about location uncertainty, where you can move obstacles from one side to another, that seems like an interesting problem to look into, and I have not so far.
Cool. Any other questions? I've actually one. So you were talking about this sort of follow-up in 3D space. What are the known algorithms in 3D space? Are there sort of known shortest path?
In 3 dimensions, even the shortest path where you cannot remove obstacles is NP-hard. Okay. So there are no exact algorithms. But there are some very nice approximation algorithms, which is basically you can achieve very close to optimal solution, 1 plus epsilon approximation algorithms. So, and they run in time, say, n cube, something like that. But I don't really know the exact.
Sure, but so you're basically hoping that you can get also to pretty good approximations.
Yeah. So our hope is we can, and I strongly believe that we should be able to come up with some approximation schemes which can guarantee you 1 plus epsilon approximation in 3 dimensions removable obstacles. But as long as the obstacles are convex polyhedrons. Sure. So if they get crazy shapes, then there is nothing we can do.
Okay, makes sense. Yeah. Cool. Any other questions? Thank you. All right, next up is Fish Wang, who is talking about security and binary analysis.
Thank you. Awesome. Okay, so good afternoon, everyone. It's my great honor to be here to give you a talk on what is binary program analysis, how we want to do this, and what we want to achieve in the near future. Thank you for whoever the good guy is that turned off the light. So my name is Fish Wang. I'm from the Sec Lab UC Santa Barbara, and our lab right now is organizing a capture the flag security competition. It's in the flying room there by the bookstore. So if you're interested, after my talk and after some other people's talks, you should go there and take a look. Okay. So nowadays, in the modern world, we are interacting with software everywhere all the time. So software powers all types of devices and systems, from PCs to servers, from SCADA systems to embedded devices. And you're going to ask me, why do those matter, right? If I'm not a computer person, why do I care about those? So you care about software because software is also powering cars, health devices, smart locks, appliances, and your cell phones that you're holding, right? So software is very close to every one of us. So through those systems and devices, software is supporting corporations, schools, offices, our government, the entire internet, and critical infrastructure. So I think it is fair to say that software is supporting every one of us and supporting our society. But unfortunately, like anything created by human beings, software is not perfect. It has defects and bugs. Those defects and bugs, they can be leveraged by bad guys or attackers for their own profit, and they become vulnerabilities. Here's a table that lists several high-impact malware incidents in the past 10 years, which are all caused by software vulnerabilities. They have all led to billions and billions of dollars of financial losses and have caused millions and millions of victims all over the world. Okay, so we are all computer scientists sitting here. We want to make the world of computing more secure, and we want to deal with the threats. So how are we going to deal with it? A very simple answer is that, well, let's just not use computers starting from today. So that's not going to work because computer is very, very important in our modern life. And if you're thinking you're not going to use computers, you're like a caveman. Okay, so we have another solution, which is, let's analyze source code and fix all the bugs. Well, so there are a couple of downsides with this. I mean, right now, analyzing source code and find bugs is very popular, but there are a couple of downsides. The first one is we don't always have access to the source code. Especially in a commercial setting where the companies, they don't want to give you the source code for you to access. And sometimes even the manufacturers themselves, they don't have access to a source code if they're using any third-party libraries in their software. Going back to that table, there is one thing in common in all the vulnerabilities. Those software vulnerabilities, they were all found in software whose source code wasn't available to the public. If you don't have access to a source code in the first place, how are you going to analyze them? The second downside is an interesting phenomenon in our field of binary analysis called what you see is not what you execute. It basically means what you are executing when you're executing a piece of executable program is the instructions in the program, not the source code. So in certain scenarios, for example, when you have a buggy compiler, it's possible for you to generate a piece of executable program that has bugs from a piece of source code that is bug-free. So if you want to find those bugs, we need to analyze the binary programs. So to make sure we are all on the same page, let me first introduce what a binary program is. Given a piece of source code, we compile it using a compiler, and then we'll get an executable program. That is what we call a binary program. That's what we want to analyze. So this piece of binary program can go into all kinds of chips or all kinds of hardware. And then in the end, they are powering those systems and devices that are around us in our life. So analyzing binary programs is not easy. It's actually pretty hard for any sane human beings to do. So because of this, we need help from tools, frameworks, or systems, right? And I'm not the only smart person who realized this. A lot of other people have realized the same problem. That's why they all developed a lot of different frameworks. And now the problem is not what kind of framework we want to use to analyze programs. The problem is, which one do we want to use? Right? You have so many, which one do we want to use? So in 2013, when we just started doing binary analysis, we also asked the same question for ourselves. There are so many such systems and frameworks, which one do we want to use if we want to analyze binary programs? And after staying a long night in DC, we gave us the following answer. We're not going to use any of them. We're creating our own. We created our own framework called Anger, which is a binary analysis framework that is powerful, user-friendly, flexible, and extensible, and also it supports a broad range of architectures and platforms. It supports performing static analysis, dynamic analysis, and also symbolic execution, which is a special kind of analysis that's between static and dynamic on target binaries. And now you're going to ask me, we all want our analysis, our framework to be the universal standard of binary analysis, but you are going to ask me, how do you know your framework is not one of the many frameworks that no one else is going to use? There's something special about us, about our development philosophy, which is we firmly believe that everyone's creative brains are very, very valuable, and we cherish that. So we believe no one should ever have to solve a problem twice, right? Based on this philosophy, we made Anger fully open source in 2015. The entire development is public. It's on GitHub. You can go there and take a look. And as a result, we'll be enjoying excellent community support. And that also attracted a lot of users as a result. So Anger has pretty good impact ever since. So it has pretty good community support. It has gave us a lot of good publicity. It is also widely used in academia and industry. So going back to our original problem, which is we want to find more vulnerabilities, right? One thing that Anger is awesome. Why Anger is awesome is that Anger gives us a unified platform that has a lot of different techniques about binary analysis implemented in the same platform. So one of the findings we find during doing research and find vulnerabilities on software is that just using a single technique is not enough. So our data set that has 86 bugs in total, by just using symbolic execution, we found 11 bugs. When we were only using dynamic analysis, which is the random testing or fuzzing, we only find 28 bugs in our evaluation. So one of our papers, the work is about integrating dynamic analysis and smart execution together. And that gave us a big boost, which found 36 bugs, which was 28% more than the baseline number, which was pretty good. And one other thing we noticed during our analysis, during our research, is that tools are not very smart. In fact, those automated tools, they're usually pretty stupid. The reason is a phenomenon that we call semantic barrier. The automated tools, they really don't care about the semantics or logic of the target program that's being analyzed. So here's a very extreme example, which is, a program tells you, give me the first 12 digits of pi and I will trigger a crash for you. When a human being sees this line, he will happily put the 12 digits of pi into this program and receive a crash. And then when any automated analysis sees this line, it doesn't know anything, and then it will just keeps generating garbage and feed to the program. Of course, it's not going to trigger any crash. So what really makes a difference is that human beings understand what 12 digits mean and what pi means. The automated tools, they don't, right? Which is only really because the programs themselves, they are designed for human users to use. And in our evaluation, we noticed that human users may reach deeper program states than automated analysis. So why are human beings better? There are just certain tasks that are so much better for human beings to do than for automated analysis. For example, we want human beings to build a certain kind of expression with respect to a certain grammar, or we want human beings to play a game and win a game. This is because human beings can benefit from prior knowledge he has, and can benefit from logical reasoning and logical guessing he could do. And right now, no automated analysis in program analysis can do this. So with this intuition in mind, we designed our system that is on top of Anger called Hackers. We put all three different kinds of analysis together, and also we asked human for help. We recruited some humans from Amazon Mechanical Turk. None of them had CS background, and we asked them to help our system to find bugs. The result was amazing. We find 56 bugs, which was 100%, which was like twice as many as our baseline numbers. So okay, this all sounds pretty amazing. It sounds like we have already solved this problem of binary analysis and finding security issues inside, right? We're not quite there yet. So there's something still missing. For example, right now we are only finding 56 bugs out of 86. Why is that the case? Right? We are still missing the other 30. And also, all those binaries in our data set, they're not very, very big. They're comparing to a browser or operating system, our binaries that we are analyzing, they're pretty small. So how far are we from analyzing real-world targets and finding security bugs there? And what is missing before we can really achieve that? So I believe one thing that is missing, well, we have a lot of things that are missing, but one of the things that's missing is what we call the binary understanding, or how do we better understand binaries. So I have briefly described that in our system called the Hackers, that we were asking humans for help. We want to inject human intelligence into our automated analysis procedure. But unfortunately, humans, they don't really scale well, right? Reproducing a human being takes a very, very long time. And then making them computer experts also takes a very long time. Imagine how much time you spend in doing all the computer science coursework, right? And then making them program analysis experts takes even more time, and it's also very expensive. All of you pay intuition fees, right? So in the future, what we really want to do is, we cannot just rely on human beings to extract their intelligence. What we really want to achieve is what we call a scalable binary understanding. Is that can we replace human beings with automated analysis and automated tools, and then we use those automated analysis to come up with insights that traditionally only human beings have, but maybe we can generate them from automated analysis. So a deeper understanding is very important. Having it scalable is even more important in the future. So that is my quest. I want to use automated analysis to generate this kind of binary understanding and binary insights. And with that, I firmly believe it will make binary program analysis easier and more scalable and more accurate, which in turn will make our world of computing more secure. Thank you.
All right, questions for Fish?
when you said that humans were better at understanding code, I was wondering what you meant with that, because automated tools are pretty good too. So, but then at the end, you also came back to the automated analysis again. So I'm wondering, what are the tasks you asked humans to do? Is it, for example, based on the names of the variables or things like that, or did you ask them to do, for example, looking at the path constraints, analyzing constraints like that, which actually automated analysis are very good?
So this is a very good question. Thank you, Taufik. There were 12 minutes was very short, so I couldn't touch that. He asked a very, very important question, was that how did we use human beings in our automated analysis? Of course, for all the human beings who didn't have CS background that we hired from Amazon Mechanical Turk, we couldn't ask them to just read targeted binary programs. We couldn't ask them to read the target, symbolic constraints. So what we did was we just asked them to interact with the target programs that we are analyzing. So one of the case studies that we did is that we have a tic-tac-toe game, and then we need to win the game before we can trigger any kind of bug in that program. So a human being did way better than any automated analysis, because for automated analysis, it makes no difference between between two kinds of states. The one is winning the game, the other one is failing the game. For human beings try to win a game initially, and then very quickly he won the game, and then our automated analysis picks up that input, very quickly figure out there's a crash. So that's something that we call, there's something intrinsic in human intelligence to tell the difference between two different kinds of program states. One is winning the game, the other one is losing the game. They are very different in the high-level logic that human beings can capture, but it's very hard for automated analysis to automatically tell.
Cool.
Thank you for the question.
So hey, Fish, I was thinking, right now the analytics and all of the metrics that are collected by Windows, Google, whatever, they're used only in case of crashes to understand what happened, recover. What if they're used to understand the behavior of the program and scale the human interaction?
I'm sorry, I didn't get the last sentence.
So, instead of using analytics just to recover from crashes, what if they're used to understand the behavior of the program from a machine point of view and use the data gathered from analytics to understand the behavior of the program and do analysis after?
I see. That's a very good point. I think you just killed one of my future research ideas. Yes, I believe it's doable. And then right now we have some people in the field of machine learning that's doing similar things. They're not on binaries, but they're on programs. One of my research ideas in the future is to do exactly that. So thank you for mentioning it.
It's good. It's a good idea then, right? It doesn't mean it's dead. Okay,
well,
one final question in the back.
Yeah.
So you mentioned that with human and your machine combined, you got 56 out of the 86 bugs. So what kind of bugs were you able to detect, and what kind of bugs were you not able to find in your program? Is there a kind of group that you could put them in?
Yeah, so that's a very good question. One kind of bugs that we were able to find, but previously the only automated analysis, when we were only using automated analysis, we weren't able to find were those kind of bugs that requires that takes a lot of state exploration, and then there's a very distinct differences. There's a very distinct difference between two kinds of states, but that difference is very easy for human beings to capture, but it's very hard for automated analysis to capture. Right. One example is you need to win a game before you can trigger a crash. But in the program, the two different kinds of states they have the similar kind of weight for automated analysis. So humans are very good at this. For automated analysis, you can see it as it's exploring a state graph. And then most of the end states you failed at the game, and only very few kinds of the states are winning the game. So human beings are very good at doing this, and then give you, hey, we want to win a game. But for automated analysis, it's just very hard. So the other side of the question is, what are those 30 crashes? What are those 30 bugs that we did not find, right? So we did some analysis there as well. One example is that you need to go so deep in the program state graph to trigger the bug that within the allotted time, we allotted like 8 hours, we just couldn't reach there, right? Or before you reach there, we already experienced a state explosion. So we have some ongoing research to better deal with that, and we'll see what we can achieve in the future.
All right, great. Thanks, Fish. Let's thank Fish again. All right, that takes us to the fourth speaker in the series, which is Yetershe. I hope I pronounced that. Oh yeah, butchered it massively. Talking about visual similarity.
Okay, so everything is working. So hello everyone, my name is Jędrzej Kozrawski. I'm a third-year PhD student at the Four Eyes Lab, working under supervision of Professor Matthew Turk. And my topic today is explaining concepts visually, continuous AI learning. So let's dive into that. And to start, I would like all of us to play a little game where we would imagine that we're having a photography contest. So there are 4 categories in this contest, each one represented by one of the images that you can see up on the screen. And obviously, what you would want to do to win is to take as original and as beautiful picture as you possible, but within the grasp of those categories. So every one of us probably have some idea on what kind of pictures, what kind of things they would picture, and which category maybe is the easiest one for you. Everyone has their own opinion on that. So let me ask you this question. How many of you think actually that this picture could potentially fit into one of those categories? Probably some of you might say yes, maybe some of you would say no. Maybe it's similar to category number 1, but that depends whether you think that the hand gesture is important or not. That's very subjective. So let me ask you this question. How many of you would actually think that this could fit into any of those categories? So maybe, again, some of you would say yes, some of you would say no. But that also depends whether you think that the arch is actually crucial in this example or whether it's not. So to put your mind sort of at ease, I will add one more image for each category. So you will hopefully have better understanding of what the category is all about to win. And now it's supposed to be more like easier to understand. So you can see that actually for the category 1, the hand gesture was not crucial at all. And the image number 1 would actually fit. And for the category number 2, you can actually see that it's not all about the arch, it's the Milky Way that was important. And the problem was that with one image, it's really hard to understand. It's the vague concept, so the second image helps. And how come that we as people tend to understand that this boosted accuracy for one additional image is helpful to us? And additionally, that is such a novel task because for me, at least, I've never taken part in any competition like that before. I can still somehow handle it. I can understand it. So what makes us unique is that we have this lifetime of experience. So we've solved a lot of problems, a lot of different problems in our past, and that's supposed to help us in the problems of the future. And unfortunately, the machine has no such lifetime experience. It was just created, so it doesn't know what to do. And so how can we help? How can we explain such a context to it? So for a basic case, what it would happen is that you know what the task is. So the task is set in stone, is unchangeable. And to give an example of that, let's talk about differentiating pictures of cats and dogs. What you would normally do is you would gather a lot of images of dogs, a lot of images of cats, and then you would train a classifier that helps you with the classification, and everything on one side would be a dog, everything on the other side would be a cat. And then you can just go on, test it, supply with another image of a cat, and your classifier should correctly predict that it's a cat. Everything works great up until the point that you see something else. Either by chance, maybe a mistake, I don't know, you're mean and you're testing your classifier and it doesn't stand any chance. It has just two options, cat, dog. There's none of the above, no goat option, nothing like that. And this is sort of an example of this lack of lifetime experience because it wasn't created for this task, so it doesn't know how to handle it, basically. So what you might suggest doing in here is just add this goat option, right? Or add, I don't know, 10 more options, 100 more options, something like that, just to be sure. And that's what's frequently being done. Those data sets, they consist of thousands of categories, millions of images. So to make you sure that you will be ready for almost anything that might be out there in the wild. But almost is a crucial aspect of that because you can never be actually, prepared to everything that's out there. There are no good data sets for images like that, unfortunately. So you might still, want to just add those to the data sets or add more and more up to the point that we will have everything out there. But that's not really an efficient approach, I think. So what we suggest is just forget about labels at all and just focus on similarities and just let sort of the image speak for itself. And I will explain what I mean by that just in a bit. And coming to the lifetime experience, how can we do that? So usually what we do, we just focus on getting the number of images, right? So you try to get as many examples as possible. And that's logical, of course. If you have more examples of dogs, then you should be better at recognizing them. If you have more examples of cats, then you should be better at recognizing them as well. But what we are suggesting in here is that if you know a lot of categories, if you know like a million different categories, that should mean something, right? So learning this next one, the million and first, should be much, much easier for you than learning your first one when you were totally inexperienced. But unfortunately, current machine learning approaches don't usually do that. So this is where we're trying to make a difference. And our research is a one-shot, one-class learning-to-learn approach. So that's a lot of technical terms that I probably won't have time to dive in those 12 minutes. This is our most recent work, just accepted to the CVPR. So the way it works is you supply it with a single image at the front. And normally what we would expect here at the outcome would be just a classification result or a label, something like it's a cat or it's a dog. And here is what I meant by let the image sort of speak for itself, because we're trying to create a decision boundary, just, sort of a perimeter around that image, that everything that will fall inside that perimeter will be classified as just similar to the one over here, and everything that will fall outside of that perimeter will be just classified as different, just like that. So now you can just go on and test your approach. You have a different cat picture over here, and it will land inside that perimeter. That means that it's similar to the one you've seen in the beginning. Now you can have a different image. It lands outside. That means it's different than one that we've seen so far. And then after many iterations, you can just fill in this space with the images, and you can see what kind of classifier you created. So with this example, we just created a classifier for cats. So you might ask, why do we need something like that? Why do we need to be able to find images similar to the one that we just seen? Because the world is basically a very strange place. And as I've shown you before, you can never be actually fully prepared to everything that you will see so far. So talking about this example, as we can see in here, maybe about self-driving cars, where for the designers of self-driving cars, it's very hard actually, or almost impossible, to actually teach the car up in front everything that they might see out there in the wild, because we're human. We're unfortunately limited by our own imagination, and I myself couldn't think about most of those situations up in front without seeing them actually. So what Tesla does currently, when it's not sure, the Tesla autopilot, when it's not sure how to behave in certain situations, it just makes the driver take over. So in this situation, what we would suggest is that, yes, okay, you have the right to not know how to behave, but this is your one situation when we will show you how to behave, and next time it's on you. You should be able to understand, find similar situation like that and remember how to behave. So we're building up on this now with some new inspiration coming from a Siamese neural network, where a Siamese neural network is just two neural networks. They're combined together with the loss function, and they're exactly the same. They have shared weights. So for vision, how it works is that you get just two images, and the output you get the similarity score between them. So the similarity score is between 0 and 1. 0 means that they're totally different, and 1 means they're exactly the same, the images. So this is just sort of a visual similarity metric to see how two images are similar to each other. And unfortunately, both this Siamese approach and our previous method suffers from this class granularity problem, where every concept can be understood and explained on different levels of hierarchy. And so I will explain visual with an example. We have two images, one of a tiger and another of a Persian cat. And if I would ask you whether they're similar and whether they're the same, most of you probably would say they're not, because, as I said, one is a tiger and the other is a Persian cat. And, you might be right, because this is the most logical first thing that comes to my mind. Unfortunately, with two examples, there might be just two wrong examples of, mammals. That's what they have in common, right? They are also mammals. So we might be thinking about that. Or maybe they're just two animals. So by that mean, they're similar. They're more similar, at least, to, banana or an apple, right? And this problem is exactly what we were facing in this competition, this photography contest up in the beginning, because first of all, it was a novel task for us, and with a single image, everything was pretty vague, so we could have, basic understanding of the task, but with the two images, if we were having one more Persian cat in here, we would be definitely knowing what is important and what's not. So current research is a solution to this class granularity problem. We're working on similarity networks. For now, it's a triplet network with 3 inputs and 2 upper ones. They will be indicating what kind of images are you looking for, so you can describe your sort of hierarchy of concepts that you're interested in, and the query would just be a question whether it's similar to those or not. So I will explain also with an example. We have now 5 images. 3 of them are Persian cats, 3 upper ones, and 2 bottom one are just different breed of cat, I guess. So if we will choose those examples like that, that means that with those 2 examples of Persian cat, we're creating a category of Persian cats. We're explicitly telling them that we are looking just for Persian cats. So if the query image comes, is a Persian cat, the output should say it's similar, right? But if we swap those 2 images, the query is no longer Persian cat. So the output of that is said it's different. But the important aspect of this approach is that if we swap those 2 images, that means that with those exemplar images, we are showing that, what they have in common, they're no longer Persian cats. They both just share the common features of cats, of domestic cats. So now this one is also a domestic cat, right? So this output says it's similar. So the general approach, the general architecture of that would be that we will have not only a triplet network, but some K-positive images to indicate what kinds of features are we interested in, and some J-negative images to indicate also what kind of things are we not interested in, and the query, of course, to ask whether it comes from positive or not. And the inspiration for that, it comes from the way the people explain new concept to one another, when you would just say, it's something more like that or less like that with an example. Like if you would describe to somebody what's a new iPhone 8 Plus, you can just say that it's like an iPhone 8, but just bigger, something like that. And the future work is choosing this optimal size of the network, so deciding whether we need negative examples, how many positive examples are actually required to perform well. Writing well-balanced loss function is also crucial in here. That's scalable with the number of those inputs. And coming up with a good training scheme. That's also crucial in this situation. So thank you. That'll be all.
Questions? None. Let me kick it off. I actually had a question
Sure.
that I should have probably asked you before, but it
Sure.
came to mind now. So when you look at, for example, in the last type, right, with these pictures of Persian and then normal cats, does the system actually work as you described it? I mean, what are the kind of things that the image processing is picking up? Is this, trying to reconstruct some edges and then look at geometric shapes? Is this purely based on color? How does it even know,
So
what's relevant in that image?
And that's a very good question. I can answer it partially because this is ongoing research. So we have the like accuracy results and everything, so we know which things it's looking for. Let me start 1 hour. So it knows which things are similar, and we can visually just inspect whether two things are similar or not. But what we want to do with that also is to look at the weights inside to see where the attention is going to. So that's sort of a future work for that, just to figure out why actually do you think that two things are similar together and why those two things are not. So to just show also to the human user that, I don't know, this is the important part that's missing sort of for that.
Okay, makes sense.
Okay.
Any other question from the audience?
I hope I'm not repeating the question, but so when humans make a, what is similar decision, that's also a lot of probably cultural background and stuff which is not in the image. So you may get different similarities because the details may be similar. In others, I mean, just the background may be similar. So you get things like that?
Yes, definitely. Now, it also frequently depends on your training data. So if somebody indicated in the beginning that, for him, I don't know, he thought that this part of the image is important, like in the example of the arch in the competition, if he thought in the beginning that the arch is important, then that's what the algorithm is going to pick up on. So that's also part of what I was talking about in future work, where we have to come up with actually good training scheme for that. So to sort of, because you can be very general in that, but then, you can understand pretty well mostly everybody, but then your accuracy is not going to be very good. Or you can understand mostly everyone, leaving off some people, but then your accuracy will be very good. So that's like sort of trade-off in here. I hope that answers your question. Okay, thanks.
Great. Anything else from the audience? All right. Thank you very much.
Thank you.
All right, which brings us to the final presentation. You will talk about data science and AI and bridging the gap. Oh, you get the laptop from him? Okay, great.
Hello.
Takes a little while before it comes. Okay, now it's back.
Oh.
It's locked up? No.
Oh, that's weird. Yeah, I think your trackpad is not working. What's going on? No, the computer itself is like not working. I guess. Is this thing? I think you just present.
Yeah, can you guys get into presenter mode without the trackpad?
Just control.
I don't know. what is this? Control something like F9 or F7 or something like that too. There's a way to switch it directly.
Okay, so now it works.
Perfect.
Nice.
Okay. No, perfect. Excellent. Thank you.
Hello. Hi, thanks everyone for coming. It's my great pleasure to talk here today. And the talk is entitled Bridging the Gap Between Human and Data with AI. So basically, we will talk about how AI can help us make better use of data. I will try to stay at a rather high level, so you won't see any like model, algorithm in it, just some high level ideas. Okay, let's get started. So let's start with decision making. Data-driven decision making is probably one of the most common things we do in our daily life. For example, if I am a doctor, I often need to make diagnostic decisions. In order to do that, I will seek various kinds of clues, like ask the patient some questions, or do some examination and lab tests, and for some hard cases, I may even have to go back and read some books. But that's fine. So I got all these clues, C1, C2, and C3. I put them together in my head. Then I can sort of make a probabilistic decision, like, okay, 90% this patient has a flu, right? So data-driven decision making is nothing new. Everyone is doing it all the time. And we are so used to it that we kind of have taken it for granted. However, things have changed dramatically in the past few years as we enter the big data era. Now we have data orders of magnitudes more than before. We have lots of data coming in different formats from different sources. For doctors, we now have electronic medical records. We have millions of research papers published online in PubMed, and we also have very cheap gene sequencing data, and so on and so forth. Such data explosion is happening in many sectors of the society. So there is no doubt that such big data can support to answer many new questions that cannot possibly be answered before. Like doctors can find similar patients based on the electronic medical record, or find the latest discoveries about a disease from the literature. However, the problem is that for most people, it's very hard for them to find the information they need from such massive and heterogeneous data. For example, if we want to find something from the literature, like how a gene and a disease are related, okay? So out of these 20 million papers, there may be a few hundred papers about that. And we need to basically search and find these papers and read them through to get the information we need. So how can we make better use of data? We know that data science is the discipline to deal with data and to get insights from data. However, the real challenge here is how to democratize data science so that more people can enjoy the benefits of data and can do decision-making with big data. We will discuss two ways to do that. One is education. Basically, we can educate more people with data skills like computer science and statistics. And another way is through AI. Maybe we can develop AI techniques to lower the bar for general people to play with big data. So let's first take a look at education. Essentially, we can ask people to take a lot of data science courses, like how to use a database, how to do data mining, or even learn machine learning to build predictive models. Then they can get inside, they can play with big data to get the information they need. And just in the past few years, a lot of data science programs, including like hundreds of master degrees in data science and or maybe tens of bachelor and doctoral degrees in data science, have been set up just for this purpose. But the problem is that for many people, it's not their main job to deal with data. They are just casual users of data. So it's very time-consuming for them to get a master degree in data science before they can play with big data. So in our research, we try to lay out a roadmap to bridge this gap between human and data with AI. This consists of 3 bottlenecks. For the first bottleneck, We call it knowledge. Basically, it's the problem of how to automatically extract the structured and actionable knowledge from these underlying massive and heterogeneous data. The second bottleneck is access. Once we extract the knowledge, we store it in some kind of database, and how can we enable users to easily access such large-scale data? And the third bottleneck is reasoning. How can we go from knowledge to the final insights, discoveries, and the solutions? So we will discuss our work on each of these bottlenecks, but we will only talk about the ideas and examples, not the detailed models for this. So for the first knowledge bottleneck, we have been working to develop models that can extract structured knowledge from text data. Here's an example in the biomedical domain. This is the title of the paper. And the piece of knowledge we can extract from this is that disulfiram can inhibit prostate cancer. Okay? So as you can imagine, a lot of such useful knowledge is buried in the hundreds of millions of papers published online. And if we can extract these kind of knowledge out, it can help a lot of downstream tasks, such as drug repurposing. For example, for this specific piece of knowledge we just extracted, we know that disulfiram is a drug which is typically used for alcohol abuse. Okay? But this piece of knowledge basically is telling us, okay, hey, maybe disulfiram can be repurposed to treat prostate cancer, right? Actually, in a paper published on Nature 3 months ago, the researchers found this hypothesis from the researcher, and they successfully verified this hypothesis. They find that disulfiram is actually very effective for a wide range of cancers. Okay, so this is an example to show you how useful this kind of knowledge could be. And if we can automatically harvest this kind of knowledge from the huge volume of literature, it can help a lot of tasks. For the second bottleneck, access. Once we extract the knowledge, we store it in some kind of database. It may still be a big challenge for users to access it. For example, if a doctor wants to find the patient diagnosed with eye tumor from a database, using the current techniques, he will end up writing a SQL query like this, which is definitely a headache for general people. And how to query data is a key problem we are studying in the database community. We have spent a lot of effort to optimize our database, right? So that we can execute SQL queries faster, like in seconds or even milliseconds. However, sure, this kind of optimization is very important for centralized computing environments like the cloud. But for those casual users of data, like doctors, they are now actually facing another kind of efficiency bottleneck. That is, it may take them days to find a programmer that can write the SQL query for them, right? So the focus of our research here is to optimize this bottleneck. We want to develop a natural language interface that can automatically translate the natural language questions or commands from users to these kind of SQL queries, which can be automatically executed on the database and get the results to the user. Okay. So natural language interface cannot, this is for data querying, but it's not just that. We can also develop a natural language interface for higher level data analytics. For example, we know that in a lot of disciplines these days, people need to analyze geospatial data, right? Here's an example of an economist from MIT who wants to analyze some geospatial data like the nighttime luminosity from satellite to study the development of China, okay? So he used mainstream GIS software, and the high-level commands he wants to do is like this. It seems easy. Then after several days of puzzling over this problem, he ended up writing a program like this. So this kind of programming is definitely very hard for some people like economics who don't have like a programming background. We are we can also, and we are developing natural language interfaces for this purpose that can automatically translate these kind of high-level commands to programs like this. Okay, so this is the first two bottlenecks. And for natural language interface, it's more about like help our user to access data and to get the information they need so that they can do the reasoning by themselves. But our machines are smarter than that. Our machines can do reasoning as well on their own, based on the existing knowledge. Here is we still use drug repurposing as an example. Let's say we have two drugs, and each one will is known to be effective for a disease. And if we know that, okay, some information like these two drugs, they target the same gene, they have similar structure, and maybe some other information, some knowledge about the diseases, like they have similar root cause, then we may automatically reason that, okay, maybe these drugs can be repurposed to treat the other disease and vice versa. Of course, the real world is more complicated than that. We will have like tens of thousands of drugs and tens of thousands of diseases, and there are a whole bunch of different kinds of relations between them, and we need to do reasoning to find the most plausible hypothesis from this space. Okay, so as a summary, we talked about three bottlenecks in bridging this gap between human and data, and we talked about how to develop AI techniques to address these bottlenecks. But I would like to note that it's not like something that has been perfectly solved. Actually, it's largely unsolved, and we just started on this. I expect that it will take like the next 10 or 15 years of my life to eventually solve this problem and develop an end-to-end knowledge-centric system that can really help end users to get insights from this kind of massive and heterogeneous data. Okay, thanks for your attention, and I'd like to take any questions.
Thank you. Questions? The crowd is hot. Okay, let me ask one. Actually, I could have also asked you that before, but just out of curiosity, what kind of, I mean, you said you're not going to go too deep into it, but what kind of models do you use actually underlying? Are these mostly statistical inference? Are you actually using deep learning models? Do they make sense? Often these sort of correlation / causality, maybe some statistical techniques are enough. Can you give us a little bit of flavor? That would be awesome.
Sure. So the main technique we develop is deep learning techniques. For example, for the first two bottlenecks, like knowledge extraction from text and natural language interface, we see that the main challenge we are dealing here is the association between unstructured text and the structured knowledge. And deep learning or neural network models, they are extremely good at handling this kind of association. So we develop a lot of deep learning techniques for that. And one unique perspective in our techniques is that we develop deep learning techniques that can be trained with weak supervision. We know that deep learning is extremely data hungry. It takes a lot of annotated data to train a neural network. But in our techniques, we develop neural networks that can be trained with some weak supervision that is way much cheaper than like the mainstream neural network models.
Cool. Maybe related to that, so since you said, okay, not a lot of supervision, so do you have to spend a lot of time on feature engineering, or really you just throw a lot of papers at it, like just PDF to text and then let it figure it out?
Yeah, that's a very interesting question. Well, a beauty about deep learning is that we are free of feature engineering. So you have the data, you feed the data into a standard model, and you will get the results. No feature engineering at all. But the problem is that it becomes another problem of data engineering. How can you engineer an appropriate set of training data for your problem at hand? And that's also the focus of our research, like how to use some remotely related data that to train our models, this kind of weak supervision. Yeah.
Thank you. Any last question, Atifik?
I think code synthesis from natural language
specification is very interesting, but anybody who develops codes or analyzes codes knows that code has a lot of bugs in it. So now, and some of the bugs actually come from specifications. People specify things they didn't intend, and when they look at the implementation, they're like, well, that's not what I meant. So what are the testing analysis strategies for the synthesized code from natural language?
Yeah, this is a very highly related question to, especially for the natural language interface for data analytics, where the goal is to synthesize a program from a natural language command from user. That's largely ongoing work, so we haven't done too much, especially from the automatic verification perspective. But this, I'm joining the Ohio State University as an assistant professor, and I'm talking with some programming language faculty members there to specify for this problem. Yeah. Thanks.
All right. Question in the back.
Yusuf, very nice talks. I have a very general question. So the way we do, right? How, let's say we need people that know physics. How do we do that, right? Someone goes and takes you become like a physicist, right? Like you learn, you go through undergrad, a master's, PhD. So we train a physicist by teaching him or her physics, right, through books. But we don't teach them by just asking them to look outside and see enough data and be like, okay, maybe gravity works like this, right? That takes too long and no one can live that long. So why do you think that this works for deep learning, but we don't do this like in the real world? What's the difference?
That's a very interesting question. So I think there are two kinds of expertise we are talking about here. One kind of expertise is domain expertise, like in physics or for biomedicine. It takes even longer to train a doctor or a biomedical researcher. So they have a lot of domain expertise, domain knowledge. Another kind of expertise is this kind of data expertise, like data science, computer science, statistics. The assumption of our framework here is that people already have the domain expertise. Like doctors, they know their job. It's just that they don't have the computational expertise to deal with big data, to get insights from big data for their decision making. So the goal of our framework is that, okay, they don't have to take like years to get these computational expertise. They can just have their own domain expertise, and using our framework, they can skip the computational part. They can directly get insights and get a job done with big data.
All right, cool. Thank you very much, Yo. Appreciate it.
Thank you.
All right, that concludes our graduate student lectures. Please come back in 30 minutes when our distinguished keynote starts. And at the beginning, we will also award the prizes for the best distinguished graduate student lecture. So speakers, please make sure you're around so that we can give you prizes. All right, thank you. Yeah, the mics are off. Yeah.